Right, so we will get started. I'm going to share my screen and then we can start. Just to confirm if you can see my screen.
Yes.
Evie, Alex, team,
Yes.
fantastic, very well. Very well. So, good afternoon, everyone. My name is Abdul Aziz Aliyu. I am with the IAGHG, and thank you for joining today's webinar. We're pleased to feature an award-winning study from a poster session showcased at the GHGT 17 conference in Calgary. The study that you will hear about is on CO₂ utilization through the production of carbonated salt nanoparticles in a rotating packed bed. This will be presented by Evie. This innovative research explores a novel approach to CO₂ utilization by producing valuable carbonated materials using advanced process intensification techniques. And we're pleased to provide this platform for Evie to highlight this study and further discuss promising developments in carbon utilization technologies. So I'm just going to say a word or two about the IAGHG. So we are a technology collaboration program and are part of the IEA Energy Technology Network. However, our views, findings, and publications do not necessarily represent the views or policies of the IEA Secretariat. So just a word about the IAGHG. We advance technology that reduces carbon emissions and accelerates the deployment of CCUS and carbon dioxide removal projects worldwide. And for more information on our activities, you can visit our website. I just wanted to flag out one of our events that we have in September, and that is the Post-Combustion Carbon Capture Conference. We're pleased to announce that the 8th Post-Combustion Capture Conference, PCC8, will take place in Marseille, in France in September of 2025. This is going to be hosted by Total Energies. PCCC is the leading global event dedicated to post-combustion CO₂ capture, bringing together researchers, industry experts, and policymakers. Early bird registration is open with discounted rates for students. And of course, we look forward to welcoming you in Marseille for what promises to be another impactful and engaging event. So I just wanted to highlight the executive membership of the IAGHG. Our members represent a diverse mix of government and the industry. The collective expertise and commitment of the IAGHG membership ensure our research remains globally relevant and technically robust. And we would like to extend our sincere thanks to all our executive committee members for your continued dedication to advancing CCUS and CDR on a global scale. So our speaker is Evie. She's a chemical engineer in CCU Technologies and currently works on developing and scaling up advanced CCU processes for sustainable industrial applications. I'm not going to go into details, but I would let Evie introduce herself more properly within a minute or two. And just a bit of a housekeeping. This is going to be a 30 minutes webinar, which is going to be recorded. So before we get started, I am pleased to introduce Alex Cross from Baker Hughes. Alex initiated the Poster Award category at the GGT conference series. He will give a short opening remark and then thereafter invite Dr. Evie to start her presentation. Alex?
Yeah,
Yes.
thanks Abdulaziz for the opportunity to give a few words. So as Abdulaziz mentioned, I didn't really do it myself alone, but it's actually a collection of one of some of the greatest industrial and academic leaders in the CCUS space that initiated this work. So we wanted to make sure that the work of young researchers like Evie are recognized in a very important event in a congregation of technical experts in the CCUS and CDR space. So it's something that we would like to continue moving forward. And I am also part of the executive committee of the IAGHG, and I really make it to my mission to have a strong representation of young researchers and young professionals in the CCUS and CDR space. So if any of you are yeah, in that category, please do continue following the activities of the IHHG, and we have many initiatives in store for you. Summer school, also the conferences, and of course webinars. And please do get in touch if you have some ideas and initiatives where we can work together to really pave the way for initiatives like this to continue flourishing in the future. So yeah, Abdulaziz, thanks for the platform. And without further ado, I'm passing to Evie to kick off the presentation.
Yes, thank you very much. Should I share my screen? Uh, Before sharing my screen, anyway, I would like to say a few things. I'm a chemical engineer. I specialize in CO2 carbon capture and utilization technologies. And my PhD has focused on phase change solvents for absorption-based CO2 capture. And also in the second part, it focused on the production of carbonate nanoparticles through the utilization of captured CO2 streams. So part of this work was presented in the GHT 17 conference last year in Calgary. So I'm currently in the postdoc stage of my, my career. I'm a collaborating researcher in Center for Research and Technology in Thessaloniki, in Greece, and I'm still working on CO2 capture and utilization technologies. So let me share my screen. Let's see. Can you see the screen?
Yes, we can.
Yep.
Okay. Is it okay? Yeah.
Yes.
Again, thank you for this invitation. I think it's a great initiative. I'm very happy to participate today. I think it's very important to support young researchers at these early stages. So let's start. As you may know, CO2 capture is considered as indispensable to reach the net zero industry targets, especially here in Europe. However, the quantities of the captured CO2 will become an important issue unless we find some ways to deal with it. So as you may also know, there are two main strategies on how to handle the CO2 captured streams, namely storage and utilization. So our team is especially interested in utilization and especially into the route aiming to recycle CO2 by treating it as a feedstock to produce inorganic particles at the nanoscale. And as these particles are of increased commercial value, this route could prove to be very beneficial for inherent industrial emitters like, say, mineral producers, because it could create some revenue and by, in this sense, alleviate the economic penalties associated with the CO2 capture processes that eventually they will be required to install. So we have been researching this route both experimentally and in model-based studies. So as I said, we have been collaborating with mineral producers in Greece. In a series of research projects. Currently ongoing is the High Record project. It's an EU-funded one. And what we have proposed is to treat part of their product which is a metal oxide like magnesium or calcium oxide, with a stream of captured CO₂, so pure CO₂, to produce the respective carbonate nanoparticles. And to do so, we have applied a very simple method. It's called the direct carbonation of aqueous suspensions of metal oxides, which are quite of high alkalinity, and thus they are prone to react with CO₂. But the novelty here is that instead of performing these reactions in the conventional equipment, we have employed a rotating packed bed reactor shown here. So I don't know if you have heard anything about rotating packed beds, and unfortunately I don't have the time to go into too much detail about the operating principles. However, I just want to say that RPBs are a known process intensification equipment, and based on experimental evidence acquired so far, we think that they could be ideal candidates to confront some of the key limitations that the conventional stirred vessel reactors have when it comes to crystallization processes. Now, this is because the RPBs enable up to 2 orders of magnitude higher mass transfer rates, and thus also enable important equipment size reductions and footprint reductions, even reaching 10 times smaller. And we know this for a fact because RPBs have been applied in other gas and liquid contact processes like absorption and distillation, and they have produced many very good results. So here you can see a close-up of the internal parts of the rotating packed bed. So briefly to explain, you have a liquid stream fed in the center of the rotor and then spreading radially on the rotating packing material surface, covering the packing material with thin films and droplets. And then you have also the gas stream, in this case CO₂, coming also from the center and then moving to the same direction. So this is a case of co-current operation in a rotating packed bed. And also here we have a simplified process flow sheet of the pilot plant that we developed and operated in our lab in order to perform the experimental study. So this is a rotating packed bed here, some vessels, some pumps. And when we operate an experiment to produce carbonate nanoparticles, we actually circulate the metal oxide suspension around the pilot plant until it reaches pH 7, so pH neutral, which would then indicate that all the feedstock has been converted to the respective carbonate. And this is the actual pilot plant in our lab. And this is the internal rotating part of the reactor. So in the framework of this study, we have also modeled the carbonation process. So this is the model structure here that can be used either to simulate or to design the carbonation process. When used for simulation, which is the case that I'm going to be presenting later on, the model predicts the process KPIs like percent CO₂ conversion, percent metal oxide conversion, and so on for a certain set of design parameters, that is for a certain set of initial conditions like certain gas flow rate and concentration, metal oxide suspension concentration and flow rate, size of reactor and so on. Alternatively, by including this algorithm in an optimization routine, then we can calculate the optimal design parameters for the whole system or for the reactor itself in order to be able to achieve certain KPIs that we want to achieve. And speaking of KPIs, in the experimental part of the study, we have adopted three of them. The first one is regarding the product quality that we produce. So it includes terms like type of mineral phase that we produce, particle size and size distribution, particle purity, and such things. The second one is about reaction time, that is the time needed to reach pH 7 in the process, which means the time needed to react all of the metal oxide precursor. And then the third one is the utilization efficiency, as in how efficiently do we convert the CO2 into the respective carbonates in the rotating packed bed reactor. So let's see some experimental results now. Uh, the first material we produced was precipitated calcium carbonate, nano-PCC in short, by carbonating the aqueous suspension of calcium hydroxide. So these are the calcite particles you can see here in the photo, and depending on the operating conditions, the mean particle size was between 180 and 440 nanometers, with actually much lower crystallite sizes. Then also, if you notice the graphs on the right-hand side here, you can see that in the RBB, we managed to lower the average particle size by 45%, or make the size distribution narrow by 50% by adjusting the liquid or gas flow rates for certain rotating speeds. So see the curve migrating towards smaller sizes or becoming more narrow. The same observations we had when we synthesized the second material, which is called hydromagnesite, nano-HM in short, which is the thin particles shown here of mean thickness of 30 to 69 nanometers. So again, this is the case here where adjusting the liquid to gas ratio at the entry point of the reactor, or by adjusting the speed, we again were able to produce much smaller particle sizes and much narrower size distributions. And these remarks are actually quite important because they show the potential of the RPB on the way to control the end product properties. So now on the second KPI, the reaction time, you can see the pH evolution curves versus time for both the case of nano-PCC and nano-hydromagnesite, where we show that in both cases we could substantially reduce the reaction time, reaching even minus 36% for the nano-PCC or minus 26% for the hydromagnesite case, by increasing the rotating speed that we employed in the reactor. So, and actually we observed that this was true for a variety of liquid to gas ratios for each and every rotating speed that we tested. And this was actually a good thing because it showed that we had room and it allowed us to explore and optimize the operating parameters for this study in order to be able maybe to accommodate both goals simultaneously, the goal of minimizing the particle size and size distributions and minimizing the reaction time. The third KPI now, we show here the curves of CO2 utilization efficiency depending on rotating speed and liquid to gas ratio in the reactor. So in the case of nano-PCC, you can see that the efficiencies were constantly above 95% in the RPB, which is considered exemplary for such types of systems, while also in the case of nano-HM, then the efficiencies also were exceeding 90%, which actually was much higher than what we had observed in a conventional stirred vessel setup where we performed a comparative study that I will explain later on. So in both cases, you can see that the liquid to gas ratio has a strong effect on the process efficiency. However, this effect becomes milder or even disappears when moving to higher rotating speeds, and eventually the efficiency becomes independent of liquid to gas ratio. This happens uh, because when we operate on high speeds, the effect of acceleration takes over and not the liquid to gas ratio, providing increased slip velocities between phases, and hence increases the micromixing and mass transfer rate, so it secures high efficiencies for the process. And here we have some model validation results. You can see how close the experimental values were to the predicted ones from the model. So, for example, the percent CO₂ utilization rate versus time for batch operation experiments presented a mean absolute deviation lower than 10%, which we consider to be quite good. And now on the comparison between CSTR setups and RPBs, in the case of hydromagnesite that I mentioned earlier, you may observe in this table of some indicative results that the reaction time per unit mass of magnesium oxide precursor was much lower, actually 1 order of magnitude lower in the rotating packed bed compared to the CSTR, while also the particle thicknesses that were achieved were up to 50% lower, and then the distributions were much more narrow, and this all happened by maintaining a simultaneously high efficiency. In the CSTR, however, this was not the case. The efficiency was very low, around 20%, and in general, the reaction was quite slower. And this happened because there were some challenges posed by the increased viscosity of the aqueous suspension of the magnesium oxide, because as the reaction progresses, the viscosity increases and causes very poor dispersion of the gas phase in the reacting medium. So it slows down the reaction. And this made us made it compelling to operate with very high CO₂ flow rates in the reactor. So we sacrificed the efficiency of the process in order to drive the reaction forward. And if I wanted to summarize some of the key benefits of the RPB for such cases, I would firstly say that the RPB enabled operation close to stoichiometric condition, reducing the CO₂ feed rate by 76%, and thus minimizing the raw material waste. And that's actually quite important because remember, in this case, the CO₂ is a raw material. We have paid to capture it, good money, and we don't want to waste it. We want to transform it completely. So it's important. Secondly, the experiments showed a 97% reduction in reaction time, allowing us to intensify the production and reduce the equipment sizes and maybe have some savings in capex or in opex. And thirdly, the experiments also revealed a potential for improved control over the final properties of the product, as we showed up to 63% narrower size distributions. So these are some of these innovations are quite important in the field of nanohydromagnesite synthesis, and that is why we have been recognized with a WIPO patent. So now, to conclude and summarize the work, we designed and improved the CO₂ utilization process. We produced nanoparticles avoiding the use of crystal growth inhibitors in the reaction process, or even size reduction techniques post-synthetically. With these experiments, we also proved that the rotating packed bed could be a potential candidate for crystallization processes and could give great outcomes. And then we also delivered a validation of a process model for carbonation. So with that, I would like to thank you all for listening, for attending this webinar, and I would like to take the opportunity to introduce you to my colleagues. This is all the team that is behind all of this hard work. These are the colleagues from Aristotle University of Thessaloniki, fellow PhD candidates and professors, the colleagues from Center for Research and Technology in Thessaloniki here, and then we have our industrial partners. And then finally, I would like to acknowledge the EU funding from SINEA for this work, and also the national funding through the program Research, Create and Innovate. So that's all from me. I'm happy to answer to any questions.
Thanks, Evie. Thank you to you and the team for conducting such a brilliant work. And thank you for the brilliant presentation as well.
Yep.
We're running out of time, but I just want to pick out a question that I have for you. Can you just quickly discuss the limitations or challenges in scaling this RPB-based process for industrial CCU?
Of scaling these processes, you said?
Yeah, of scaling this RPB-based process, that's right.
Yeah.
What are the challenges or the limitations that, from your point of view?
Yes, I think there are some challenges, mainly associated with the fact that in order to, synthesize the carbonate particles, you need to have aqueous suspensions. And the thing is that you have to handle the volumes of water, which you would like to minimize in this process. So you would have to design a process to operate with highly concentrated suspensions of solids. So this would you know induce a lot of thinking on what packing material to select, issues on how to manage the pressure drop in such reactors and stuff like that. And also another thing is what happens after the 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 particles are produced, are synthesized. What happens with mostly drying the particles, stuff like that. So again, you have to handle large volumes of water. So you have to fine tune and make some, trade-offs between operating dilute suspensions or so you won't risk, large pressure drops or high operating costs. But then you have to consider other things like the cost of drying of the products and so on, I would say.
Thanks, Evie. That was a very good session. Thank you for honoring our invitation to come and present your work. And I just wanted to also say a very big thanks to Alex Cross, Baker Hewis. Alex was the initiator of the entire GHGT Poster Awards. Thank you very much, Alex, for all the good work that you've been doing. This is very much appreciated. And on this note, have a very good day, everyone. Thank you for coming on board. And hopefully we'll all meet shortly in one of the IEGHG's event. Thank you. Bye.
Okay, thank you.
Thanks,
Bye.
Evie. Thanks, Alex. Yeah, bye.
Bye.